Is this muted or not?
Hello, team.
Hello, good afternoon.
Can you hear us?
Yes, we can hear you.
Perfect.
If you want to turn your camera on and do
Sure.
a check of that, would be recommended.
There you
Yeah, there it is. Yeah, there it is. There it is.
Nice.
Hi, nice to meet you.
So,
See if my camera lets me today. All right, you guys all ready? Do you guys have any video that you are going to be playing during your presentation?
Yes, we will. It's in our PowerPoint, but just in case there's a little lag, we had to do like some modifications, but I think it should be able to work for everybody.
Okay, and does it have sound?
No, it's just no sound. We're basically just gonna narrate through the video.
Okay. There's just a certain way you got to play it if it had sound to it.
Just turn this on. Let's see. Is it okay we could just share our screen just to do a quick test?
Absolutely, this is your time.
Alrighty. Let's do a quick test with this current one.
We can see your screen.
There it is. Just doing a quick check with the video. I have a question, ma'am. Can you see the video like playing?
At the moment, no.
How about now? There should be like a blue and yellow color.
I can see it from your screen, but it's not like filling my screen,
Oh, okay.
if you will.
I mean, we still have our screen, so either way, it doesn't matter.
Was this screen share?
Yeah.
Yeah.
It's also pretty difficult to see anything on that chart. So if I were you, I would share it through Teams rather than your camera on the screen, because I can't tell anything
Oh,
what
I'm
that
not
chart
sharing
is
the
supposed to
screen.
be.
Yeah, that's what I was wondering if like that screen is shared.
I thought I was sharing my screen.
You were earlier.
Share desktop. There it is.
Okay, yeah, that's much better. Thank you.
Okay, thank you so much.
Okay.
And then one more quick check before we start. There it is.
Does it stop sharing whenever you do that?
Did it stop sharing by any chance?
It
It
did.
did.
It stopped sharing
Okay.
your screen.
Yeah, so when I go to presentation mode, it stops sharing.
Mm-hmm.
So let's try. So let's do. I guess since we're here, let's share the screen.
If you want, I can bring out my laptop, join on the Teams, share the PowerPoint on there, and we can change the slides like that, and yours does the presentation.
All right. How about now?
Perfect.
Okay.
Perfect.
And let me see if we can see like us going through the slides. Are the charts now easier to see, even the tables?
It looks fabulous.
There it is.
Very
All right, perfect.
And your video is playing.
Awesome.
Yep, you're good.
Alrighty then. I guess it's time for the presentation and get this thing started. Thank you.
Yeah, so give me a second. Well, we'll kick things off. Excuse me. So I want to say welcome to University of Texas, Rio Grande Valley, and your team name, Society of Aerospace and Robotics Engineers. My name is Teresa Martinez, and I am the project manager for NASA Mines. And we also have Amanda and Carol, who are part of the NASA Mines management team. And then we'll get to the judges in just a minute. And first thing I want to start with is, a big congratulations on being selected as a finalist team. Just making it to the finalist round, that's a huge accomplishment. And you guys should be proud of yourselves. And that's a really big deal to just having been selected as a finalist team.
Oh, thanks so
I want to give you
much.
Thank you.
Thank you.
I want to give you a quick shout out and congrats for that. So a couple of quick reminders. This session is going to be recorded. We can't have anyone on camera that has assigned a media release. Presentations can only be done by student team members, not faculty or mentors. You will have 20 minutes to present plus 5 minutes for Q&A for a total of 25 minutes. If you use your full 25 minutes for the presentation, there won't be any time for Q&A and judges won't be able to ask any clarifying questions. You will get a notification at 20 minutes. So be prepared, that's going to be a voice comes on, that says, 20 minutes, your 20-minute mark. And that's just to make sure that, that you're aware of that. And then there will be a hard stop at 25 minutes. So, but once you're done with your presentation and Q&A, please don't log out. We want you to stay on camera for a few more minutes. We want to get some team photo. We're going to be doing screenshots. We want to ask you a couple of questions about your experience with the NASA Mines. And with that, we can start the recording. And judges, if you can turn on your cameras for a minute so that we can introduce you to the students. So our NASA judges today are Heather Romani, NASA Launch Services Program Avionics Lead, Harry Sota, Mechanical Engineering degree, Master's in Materials Engineering, working for Commercial Crew, Paris Bishop, NASA Test Director for the Artemis Program, and Cody Farinacci, Engineering Project Manager. So you've got quite a bit of experience here that you're going to be presenting to today, and that will be, evaluating your project. So judges, you can turn your cameras off until the Q&A, and students, you can go ahead. Your time starts now.
Awesome.
Good
Thank
luck.
you so much. Alrighty. Y'all ready?
Yep.
Awesome. Well, good afternoon, everybody. My name is Martin Lopez.
I'm Miguel Torres.
I'm Jonathan Ramirez.
And today we are the Society of Aerospace and Robotic Engineers presenting the AMMB, or also known as the Analytical Model Microgravity Bioreactor. For today's presentation, I just want to introduce the team that has worked really hard throughout this whole entire academic year. We had so many students from freshmen, sophomores, juniors, and even seniors coming by with this team and creating this collaborative project that's collegiate with both engineering and biology. And I want to congratulate our team from working with the structures, research, and the telemetry side of this project, which makes this product into a reality and also making it to the final stage of this project. For the outline, we'll be going over project overview, the objectives, structures interface, electrical interface, as well as going into the cost of the system, some ideas of the hierarchy that's behind the system, and some trade studies we have done, and lastly some conclusions and lessons learned, and as well as the Q&A session for the judges. So, when working with this project here at SARE, we were looking for a project in the summer and have met with a professor named Dr. Saratna Guadarrama, who is one of our advisors from the biology department and has taught us this incredible thing about, working with model microgravity. Now, in the Artemis mission, we are exploring into going into a mission that's based on research and exploration in space. That includes going into the moon and Mars. But there are some challenges present for the astronauts. And one of the issues is dealing with, bacteria or microbes that are on board the shuttle during space travel, which can cause some harm or cause illness to the astronauts due to the model microgravity conditions or the microgravity that's in space in the International Space Station, Mars, or lunar as well. This bacteria that we were looking at especially was the Pseudomonas aeruginosa, which is here in figure number 1. The Pseudomonas aeruginosa is a microbe that our professor has been looking for a couple of years, and it's something that we would like to understand and how it expresses in microgravity. So working with this project kind of taught us both the biology and the engineering side of this project. But what is the solution in looking into this research? Because samples are going to be very expensive sending into space due to payload and rocketry. So a best deal of the solution would be the clinostat. This system, basically in figure number 2, is an emulator for microgravity conditions. And it also contains this product called the HARP, where the bacteria, fungi, plants as well, samples that could be into this small disc that's right here on figure number 2. These discs can contain these samples and kind of give that emulation of MMG, which is model microgravity. The cost of these products go from $6,000 all the way to $13K with software and encoders, and the total sum of this product is at a high cost at $16,000 to $22,000. But here in SARE, we have the goal of helping our professor and also helping the Artemis mission with making a product that's both cost effective, computer aided with technology, and as well as enhancing the research capabilities for space medicine research. And the objective in the engineering side that we wanted to introduce as a team was to create a product that was automatic injection, the vibration monitoring, as well as the multi-platform compatibility and low maintenance that this product deserves, as it is important to look into this research for astronauts in the future of space travel. Here's just a sub-assembly of the entire product, just a quick overview of it. Here we just have all the 3D printed parts, the brackets, as well as the stepper motor. The DC brushless motor that we have used for this product, the bevel gear system that our structures team Johnny will be going into detail with the bevel gears, the carb itself, or the high aspect ratio vessel. And in this next slide, we'll be showing on the right the injection side, which is used with a linear actuator that will be pushing a syringe, as the main focus of this project is the idea of avoiding shear. With the avoidance of shear, we want to understand that there is at least minimal oxygen into the bacteria to have a great focus on this study. So controlling not just the HARV, or the high aspect ratio, which is the disc, but also the linear actuator with the syringe that's injecting inside into the high aspect ratio vessel. This is just a quick system hierarchy that we've been working with the entire project, from structures, telemetry, and research, which will be now detailed in the next couple slides.
So with the structure interface, we really wanted to focus on how we can reliably transfer that power, and for that we decided to go with a bevel gear configuration. In doing so, we did find that it is a very reliable thing, provided the current function that they use, which is a band-driven shaft system. To further this, we also decided to go with the linear actuator to be able to monitor how the speed changes during the injection process, because that was something that the professor had expressed to us was a limiting factor throughout the research, and how during that injection process, changing that speed could cause some unwanted variables during the actual testing of the product. We did look at some things like PETG for the actual 3D printed parts, and we wanted to look at the shear modulus, as most of the stresses that would be present would be shear stress due to that torsion. Another factor that we wanted to take into account was the thermal properties of these materials, as part of the process of the testing phase is going into an incubator to be able to incubate that bacteria and let it grow into a culture.
As for the electrical side of the project, the core operation of the system is a microcontroller called ESP32, which has Wi-Fi and Bluetooth capabilities, which allows us to have a two-way communication between the UI and the electrical side of this project. So over here in this slide, we see the quick electrical circuit, or the wiring diagram, which puts everything together. That big part right there will be the ESP32, and right there on top is a little H-bridge, which controls both the motors, the DC motor and the linear actuator. And as mentioned before, we do have a gyroscope sensor which detects any vibrations within the system. I'll go a little bit more in detail in these following slides. So to control the motor, we do have this H-bridge, more specifically the L286N, which is a dual motor H-bridge controller. And what we do to control the motor accurately is this process called PWM, which controls the speed, and also the module allows us to control the direction. So in this case, we created a table by measuring the voltage given by the RPM, the RPM given by the voltage we need, and then compare that to the duty cycle that we need to put into the module to control the speed we want to do. For example, if we want to get around 30 volts, the duty cycle will be around 40%. And then on the code, as pretty much that math that we're doing. So on the graph, there's an equation that we use to get that exact duty cycle that we need for to control the motor. And this applies for both the linear actuator and the DC motor. And there is a gyroscope sensor in the system which allows to detect for any minor vibrations or any noise around the area. That way the user can actually visualize any variance in the data, just in case there's like a small sudden bump into the system, or if the hardware itself is causing vibrations. So that's the type of data that will be sent to the UI or to the software side of the system for the user to analyze and understand if there's any variables that need to consider. As for the software side and the user interface, we are using this app builder, this framework called SARE 2.0, and this is built upon a front end and a back end. The front end being based on web development tools, which is HTML, JavaScript, and CSS. The back end will be Rust. It's very versatile, especially for its memory optimization properties, which is the reason why we went for that for our project, which is trying to use as much memory. But another thing, this app is available for anyone who's planning to use the system. So yeah, now I'll just show more how it all works together. So right here, this is the quick overview of how the software side of the ESP and the electrical side of the ESP communicate with each other. So on the left side over here, you can see that that would be the UI, the SARE 2.0, and any data that needs to be sent to control the motors will be sent to the ESP, and then from the ESP it will be sent to the other ESP using a protocol called ESP Now. With this protocol, the ESP will process the data received from the UI, and then it will convert it to the required PWM or the direction it needs to control the motors. So the device will be the entire electrical system, and then it also receive data from the gyroscope and send it back to the UIs. That way the user can visually see any variance in data in regards to vibrations or rotational change. So this is pretty much like the quick overview of how the system works together with the UI and the electrical side. And later on we'll demonstrate how that works.
Yeah, we'll let them know.
Okay.
This is just a quick overview with the cost. Now we have spent around $2,600 with this R&D phase of our project, buying materials, buying the filament that we need for our structures team. Some ideal things like the barrel connectors, the electronics, the ESP32s, which is microcontroller, the H bridges. All these products were spent on R&D phase, but this income didn't just come from NASA Mines as a sponsor. It also came from our College of Engineering and Computer Science here at the University of Texas, Rio Grande Valley, offering us some income, and as well as our first year of looking into a sponsor called Seven Brew, who are a coffee shop that is here local in our region, and as well as some fundraising that we did over the year of the academic year. We did notice that, as we worked with this project, at the beginning we did mention this is a project that's over $10,000, and with our research and our R&D done, we have noticed that we could decrease the price of this product into $509.99 for the cost of just building this material.
So to be able to validate the materials that we selected, being PETG, we decided to do hand calculations as well as FEA to compare and see how close the actual numbers came out to each other. And we found a 7% error in doing so. With this, we also found that the highest stress that would be achieved is around, I believe it was 1 megapascal for this piece up here, and around 2 megapascals for this piece over here. I could be wrong on that. It might even be lower than that, to where it was 0.1 megapascal and 0.2 megapascals. And in doing so, we actually did find a factor of safety of, I believe it was 4. And where we did do research and checked the machining handbook and found other resources to validate that the sheer yield strength of these materials would be able to handle the application's stresses that were involved.
Here's the continuation of our R&D with engineering research. Here we have a CFD simulation of how the high aspect ratio vessel would be at 10 RPMs. But including with this, in graph number 2, we were learning that, with the idea of avoiding as much shear as possible from Dr. Guadarrama, there is a relation between on how much RPMs there are as well as the temperature. So in many papers, there's 10 to 15 RPMs. That has been a standard on all these papers working with clinostats. But for this region, we have done 10, as it is the minimum temperature, as shown in graph 2. But here in video 2, as you can see, if we started at 10 RPMs right away, there's will be a lot of vortexes causing a lot of shear, with the centrifugal force, and as well as shear with the rubbing of the walls and the liquid, which the sample that we use is water, which is very close to the viscosity of the bacterium, which all shows that both the temperature, the centrifugal force, all have a factor which we are trying to avoid.
So in this trade study, what we decided to do was try to replicate how the current system of the clinostat from a company named Synthicon works. And in doing so, we compared some of the filaments that were being used in those. And the heat resistivity for ABS was the highest, but we did find that a lot of the other mechanical properties for our PET-G that we decided to go with, like the yield shear strength, as well as the tensile strength, were higher in the PET-G than the ABS, and that provided us a reason to move forward with PET-G in our testing. Another reason was because we had the old system, it was a band that would wear out, and that band that would wear out, it provided a little bit more maintenance, where the bevel gears that we were using have a longer lifespan that would only need really more lubrication than the band would, and it provides less slippage as well.
Another thing we looked into was the types of mortars we should use for our project, especially to rotate the harv. One of the ones that so here are the types of mortars we looked into, which is the brush DC mortar, brushless, and a stepper mortar. We mainly went for the brush mortar because of a built-in quarter, which we didn't end up using in the end. But the one that we had available to us had really high torque, which was known to go in very slow speeds, but also enough for us to keep the mortar moving for a very long time. So that's pretty much our study.
And now this is the demo that we're going to be showing here in the actual live feed here. So this is the actual prototype here of the high aspect ratio vessel, which is this round cylinder that we have here. And this entire thing is the clinostat that we're working with this entire academic year. Would you like to give a quick demo with the injection?
We do it in the end.
Are we doing it?
Yeah.
Alright,
If
sounds
there's
good.
anything else to present, go ahead.
Yeah, the last things we do want to talk about are just the future works. Now, as we're taking into account with the Artemis mission, we do want to secure, the health systems of the astronauts and with, these microbes traveling with them. Either it could be with the lunar mission, Martian mission. And we also want to use this not to just replicate model the microgravity, but also lunar and Martian as well. And these enhancements could help with, collecting data on understanding on how these microbes or bacteria like the Pseudomonas aeruginosa express in these different gravity environments. One last thing, this is also a quick prototype that we have as well, called the HARP-E model, which will be the future work that we recommend for the future. And lastly, the conclusion is that the AMM system, we want to focus with space health research, as well as having a cost-effective device that could help space medicine, key crews with mechanical systems, smaller motors, more safety presentations, and as well as a potential new structure. Thank you all, and we would like to welcome the judges for a Q&A. Thank you very much.
Do you want to demonstrate real quick before I do the
Sure.
Q&A?
Of course.
Or, yeah.
Do you want me to, after you do the injection, to remove it?
Yeah, that'd be great.
Okay.
All right, so first we're gonna demonstrate the linear actuator motion, pushing in or injecting the bacteria directly into the harv here. This will be the harv aspect ratio vessel. Here, if you don't mind.
Yeah, I could take out the camera if you want.
All right, yeah.
Yeah, I got you, man.
So here's our harv system, as I mentioned, the high aspect ratio vessel. And this will be our auto injection system connected to the linear actuator. So right now I'm going to demonstrate the pushing motion of the syringe into the harv right here. So, and to do that again we use a protocol. If you want to look over here real quick. So right here we have like a separate computer to control the system. It's not directly connected, so it's all fully wireless. And with that I can control it. Put it back over here so we can show. All right. Ready?
Yeah, ready.
Here it goes.
There you go. That's the auto injection that we were introducing with our products.
There you go.
And that would be basically just traveling the bacteria from the syringe, which is helping with the linear actuator to help prevent as much shear as possible. And as soon as that's done, the scientists or the researcher would remove the syringes and will commence, the spinning of the high aspect ratio vessel.
You want to show that?
Yeah, sure.
I'll do it over to
Let's do one more demonstration for the audience. Here's the injection.
Cool.
There it is. Alrighty then.
That's pretty much it.
Alrighty, thank you so much.
Well, did you want to spin it at all? Because I was gonna.
That'd be great.
Yeah,
Really
actually,
quick.
let's give the audience, also the clinostat spinning as well.
So you do have to remove the actual adapter that connects the actuator to the syringes, and you have to remove the syringes as well.
You got it.
It should just pop right off.
Yeah. Yeah, it's close. Got it.
And so this part is purely for the testing portion whenever you're actually putting this device inside the incubator. And so a lot of these parts we wanted to be able to make removable for that reason.
Yeah, big factor is lower maintenance, exactly. For for the future scientists or researchers with space medicine.
Ready to roll?
You ready to roll? Yeah.
Here it goes.
No pun intended.
So another thing we also incorporated into the system is a slow startup, so to prevent any shear force mentioned.
Of course.
So reduce as much as we can. So from what I would do naturally was just start slowly and slowly build up to the speed required to do. So right now I'm about 30 RPMs in forward motion. And here we go. It's going. Oh man, technical difficulties.
Technical difficulties?
Yeah, technical difficulties.
Is there anything connected on the H bridge? Just want to check up.
No, it's all good.
Was it when they got yanked earlier?
Probably.
Probably, yeah.
Yeah.
Yeah, when we're displaying this entire setup here for the judges, one of our members is all peanuts, and he accidentally yanked one of these cables, so that's probably why we have these technical difficulties. But yeah, I guess in the meantime, let's just move to the Q&A.
Yeah.
In the meantime, since you could look into that.
Yeah.
Alrighty. Well, thank you so much for listening. I guess it's time for any questions, concerns, from what we just presented. Thank you.
Yeah, so judges, go ahead. with,
20
any
minutes
questions.
just ended, guys. 20 minutes just came up.
Oh, really? Just exactly 20?
Perfect.
Exactly 20.
Awesome, guys.
Good job. So excellent job putting this together. This is a neat, multidisciplinary challenge that you took on, both with electrical and mechanical engineering, and then the bioreactor part. It's pretty slick. So it's nicely done developing that. What inspiration did you have? What requirements were you working towards when you were putting this together?
So, are you asking about what inspired us to work into this project, or?
That a little bit, and then what specific parameters were you looking for? RPMs, injection times, that type of stuff. Wanted to see kind of how you approached specific requirements on the project.
Yeah, I guess for the inspiration side of things, sir, we were inspired by looking what's effective for the future of Artemis. And during the summer, as a team, we were actually asking a lot of professors here in our university to understand, what's a niche thing or a needed thing. And that's where we came by with Dr. SARE who, inspired us and also, involved us with this project with the clinostat. The reason why we chose this because we wanted something that, not just a project that's just cool, for the students to learn, but it's also multidisciplinary, as you mentioned, but it's also impactful too, because this is important research, and we do want to continue this research, for all the astronauts or explorers that are going up into space. And understanding these microbes or this bacteria that travels within the space shuttles is a huge factor in causing a slowdown with research. Now, with parameters that we were looking into, one of the main ones was RPMs, and we wanted to have an understanding, RPMs based on the motor with how it spins. And we also, like I mentioned, in future works, we wanted lunar and Martian. However, we had a talk with our advisor, Dr. Marquez, who is our professor in the PhD department for the mechanical engineering department here in the engineering building. And he mentioned that depending on, these types of motors you're using, the setups, it all varies. And he recommended us just to go with a standard of 10 to 15 RPMs that Dr. Wadham supported us with. So that's one parameter. Another parameter was, the flow that's going inside this HARV, or the high aspect ratio vessel. That's why we did the simulation. So yeah, show them the. So we had an original version that's made out of acrylic, as that's how they're usually made with this material that's clear. We wanted to also focus with the shear inside going on with the rotations, with the bacteria inside, and that's why we did CFD to understand what are the effects. We also have that graph, understanding how shear affects both with the rotation of the walls with the fluid, and as well as the centrifugal force. And I think other parameters were maybe some in the material side too, right?
Yes.
Jonathan?
So a lot of the other parameters that were at play were the shear forces that were experienced throughout the torsion and due to the motor, and we really wanted to look at that in the shafts, and that's what the FEA was on. The hand calculations that we did match up very closely. We only had a 7% error, and in doing so, we found that we were below the shear yield strength, and that let us move forward with the project. Another parameter that was really concerning for us was the thermal environment that it was going to be subjugated to. Since the bacteria has to grow, it's put in an incubator during after the injection process, and while it's spinning, they put it inside an incubator so that way it's able to have that environment for that bacteria to grow. So that was another reason why we were looking into a lot of the thermal properties of the materials used.
Excellent, thank you. And then one more comment, another step that you could consider for future work, trying to automate the injection and then the release of the injection mechanism from the biostat is probably good to look into.
Yeah, definitely.
Gotcha, yes sir.
One of the future things we hope to do is incorporate another sensor here that will actually measure the distance covered and the amount it needs to do required by the user. As the user wants to go like halfway or all the way, that's something that you input in the UI, so that's something we've been looking into.
Thank you very much.
Thank you so much, sir.
Is there any other questions?
Harry, you're muted.
Sorry, this was a great presentation, and I want to commend you all for all the hard work. I particularly love the assembly video. I know that took a lot of time, but I really appreciated it. Really quick question. You were talking about PETG. What part, why you chose PETG, and what part, is it the incubator? What part is made out of PETG?
So the PETG is actually the whole shell here, as well as these mounts. Okay. The shafts are also made out of that material, and also this mount over here for the actuator, as well as this mount for the PCB board. So pretty much anything that wasn't purchased to actually incorporate into the model, like the electrical parts, mainly the electrical parts, and like also these bevel gears. So these bevel gears were actually, I believe, they're steel, but I forget exactly what steel they are. I know we had it written down, but these bevel gears were also ordered, and so we also did look into the properties of these, making sure that they would be able to handle the actual stresses that were induced on them, as well as the thermal environment that it's going to be subjugated to. And so pretty much anything else that would had to be custom made is made out of that PETG material.
Great. And what is the material of your chamber for the bacteria to grow? The little chamber over here. Yeah, that.
You can talk about the original one.
So this original one, sadly, we had a complication with it, and we were short on time. So this threading at the back of it didn't end up working well whenever we tried to get it tapped at the machine shop. So this is pretty much the model that we really wanted to have on to this physical model. But this one is made out of acrylic, and so it's molded. We took a PLA.
Resin printed.
This one's not resin printed.
No, but the one with resin, and it was made in silicon mold, and then the acrylic was poured into it.
No, it wasn't resin printed. It was PLA printed.
Okay.
Yeah, so it was PLA printed first, and we made a silicone mold with that PLA print. And from there, we were able to make this resin poured mold. And so we did incorporate gaskets in here to account for any leakage. And the reason why we really didn't want to go with a printed HARV model is because with 3D prints, you do get a porous finish, and that will allow air to escape, fluids to leak, and that would create a lot of complications throughout the process. And so this one though is acrylic, and is what we were hoping for the final product.
Very interesting, and none of those materials get affected by the incubation temperature of your culture.
Yeah, okay. So creep is typically experienced in PETG around, I believe it was 60 to 80 degrees Celsius, and the incubation process takes place around 20 to 30 degrees Celsius.
Oh, no problem. Okay, great. Hey, thank you again for the project.
That is fun. 25 minutes. We went a little. I want to let them finish answering your question.
All right. So we need you guys to stay on. I was able to get a screen capture. You have a large team, and so I was able to get we always try to get a team picture, and I was able to get a screen capture there. But do you have any other? I would like to get another one with the hardware in front of you. Do you have any other team members in the room that want to join in the picture?
It's just us here.
It's just us, and currently we have folks in class. Currently, unfortunately, they couldn't come by to the
Yeah,
presentation.
sure, that's fine.
Yeah, I'm actually late.
That's
Are
fine.
you late to class?
Yeah, I just wanted to ask. So if you guys could arrange yourself around the hardware so that we can get a screen capture here.
Do you want
And we're
to
missing somebody.
move the camera back a
Somebody
little
stepped
bit?
out of the-
Yeah. Let me see it as flat as possible.
Yeah. That way we're able to get like most in frame, Is
Let's
that
have a
good?
word.
You wanna move this just so we could have like a reference of how?
How it looks. Well, we
Yeah.
can look up at the screen.
Yeah, we
quick.
can look up at the screen.
Yeah, let me see. Right there's about good, right?
Yeah.
Okay. All right, give me a second to save that. 1 minute. And now, a thumbs up or a little more energy into the picture, or
Yeah. Okay.
take
So-
another one.
So this is from our school, the Visa, because we're we for volcanoes.
Yep.
Yeah, we'll do
Is that good?
Yeah.
Okay.
Yep, that works. Okay. All right, and again, give me a second to save that. Okay. All right, so, and then just a couple of questions. Wanted to know, like, why did you decide to join the NASA Minds competition? Like, what drove you to want to be a part of this?
Well, our team has actually been in NASA Minds for the past 3 years actually, and it's a fun project, not just because it's engaging with the Artemis mission, but something that I've noticed that these projects come by with NASA Minds, you meet a lot of great people and make this path of finding new friends who have the same interests as you, wanting to build something new from the start and making something that's incredible as a product. And here in this project, like we've made like lifelong friends, and that's kind of like one of the heaviest things I would say for me why we like to join NASA Minds every year. It's both impactful, make friends, and it's honestly just something really awesome just to be around with.
Is it Chinese?
Yeah, of course, man.
Okay. You go.
I mean, something that I really enjoyed joining this organization in is you really do see people from a lot of the other schools come by as well. It's not just mechanical, electrical, or biology majors all in one room. It's like everybody all together working for this common goal, and I feel like that really opens our eyes to how impactful it is to have that diversity in a team and how that can really help out for a project.
And if I may add to that, that's what I wanted to say, that it's just that challenge that we're all kind of looking for, because we all have this passion like in engineering, so like just having to contribute something big, such as the Artemis mission, is something that pretty much connect us all to something that we'll be using later in the future. But I guess like one of the big challenges this year will be like working with like biomedical stuff, and just like from engineers we're like a what?
And we're like biology, but we're not afraid to take on the challenge. But we're always here to like accept any challenge on our way and make an improvement and innovations.
Excellent. And what kind of skills did you learn from participating? That can be technical skills, or it can be more soft skills like communication. What did you learn from participating?
I would say like a lot of communication skills, especially since, as I mentioned before, we do have a lot of people come from different backgrounds. So just having to share from what we know to them and kind of go back and forth, like exchange our knowledge with certain area that we can like something like work together. Um, so that's like one of the skills that's really important in our club. But I guess another thing would be like also technical skills because we're always trying just new technologies that are coming out. Especially for in my case, I did a lot of electrical side. So this new module, the ESP32, that's something completely new to me that I was able to just pick it up and like learn everything I need to know to make this thing possible. So that's like another thing and that was really helpful, you know.
I would say that in terms of soft skills, definitely communication and being able to manage a team. I actually joined as a member last year's competition, and I was able to be a lead for structures for this year. In that, I wasn't too sure how I would perform as a lead, but I really did want to challenge myself, and I wanted to help out the project in what I do. And in doing so as well, I was able to help out a lot of the other members with some of the experience that I had. So I had a little bit of experience with 3D printing, and I was able to help them with a lot of the 3D modeling to have those prints realized. And on top of that, I was able to hone my skills in the 3D printing and the modeling process. On top of that, we were able to actually delve into a lot of the mechanics of solids that was employed for the hand calculations for the actual shafts of the system. On top of FEA, that's not a class that I have taken before or that a lot of the members have taken because it's an elective here at the school. And so I wanted to personally reach out to some upperclassmen that I knew that have taken the class and have gone through the steps already that could come and help us and show us how we can really perform an accurate FEA model on this project.
I guess just for me, the biggest thing was leadership. As a president of this organization, it's incredible to meet with new people, especially working with these talented, young individuals here in this organization. But it also taught me, different ways of thinking, not just thinking about, what we've done in electrical or software, but also keeping in mind like what's going on with the structures team or the research team. Having like all these teams together and managing all these teams together just made me a better leader. Of course, there's some mistakes on the way, and soft skills was something that was boosted for me as well, and as well as a confidence boost as well with presenting, talking to new individuals, and I guess for technicality, I guess it was just more the fluid dynamics and CFDS. This is a course that's not often given in our school, but thankfully we do have professors who give us support, ideas, equations, and a push of starting a learning of new skills.
Excellent. You mentioned conference. Have you guys submitted this or presented at a conference?
Not at the moment, no ma'am, we have not.
Okay, all right. I just wanted to ask about that if you, because some of the teams do. Some of the teams either submit their papers, posters, or since you mentioned it, I just wanted to ask about that. So, okay. All right, well, good job, guys. And yeah, you guys have typically done well over the years, so congrats again on being a finalist and for having a team this year. And we will see you at the award ceremony on Friday at 3 o'clock Eastern time, and we will send out a link so that you can join us for that.
Sounds great.
All right, thank you so much. Thank you for your time.
All right. Bye, guys.
Thank you and take care.
Bye. Have a good day.
Bye, y'all.
Thank you for taking the time.
Bye. Thank
Bye-bye.
you.
I think that went pretty well.
I think I went pretty well too.
All right.
Is it okay if I dip in the
Just
tip?
dip in.
Nah, we take everything.
We'll take
All right,
everything.
good.
Thank you guys. Thank you.
Hold on, quick picture. Just a quick
All
picture.
right. Quick picture's fine.
Can you take a quick picture of us? Quick picture with the heart. Finish.
Oh wow.
Dude, imagine that thing rang. That thing was on this thing was on the entire time. Stop doing your
Hold on.
Dude, come on, let's go. I gotta get to class. Come on, guys.
Why didn't you
Come on,
quiet it down?
No, it doesn't matter. It didn't like. Okay, we want a picture. Okay, watch it.
Who called though?
I don't know. Picture. Yes, go.
All of yourself. Hell yeah. We're gonna do one without the visa.
No visa.
Yes, we're gonna. Okay, now one with the visa. Wait, this one, because this one looks good on Instagram. You do visa up. You're not doing visa up. Oh yeah, it's good. still going.
I like it. Okay, I took like 20.